Greetings! I'm here to talk to you about a problem that I faced when working on grapheme. It has to do with the fact that numbers in JS are always floats, right? So if I want to, so they're always 64-bit floats. So I can happily store, 2 to the 308, but I can't store, 18 quintillion without it, like as an integer, without it rounding it to the nearest float. And this is sometimes a problem. I've decided for grapheme that it's only going to support integers in the safe range, which is between -9 quadrillion and 9 quadrillion. The actual value is numbered a max safe integer, which is 2 to the 53 minus 1. That just makes things easier. But there are still some problems to be faced even when we restrict ourselves to this range. In particular, I've been writing routines for checking whether a number is prime via Miller-Rabin test, and also checking whether checking factorization of a number, finding the factorization, which uses Pollard's row algorithm. And both of these functions require the use of basically calculating the exponentiation modulo some base m. So, for example, if we have b to the exponent e modulo m, this is used in basically both of those algorithms, and this can be computed quite efficiently. The way that works is you basically use exponentiation by squaring. So, for example, b squared mod m. This can be calculated just by doing b times b mod m, and then if we square it again, we get b to the 4 mod m. And then we can repeat this process, and obviously this works for powers of 2 exponents, but for exponents that are odd or aren't powers of 2, we can actually break it down into its bits, and then do the repeated exponentiation, but sometimes instead of squaring, we multiply by b instead of itself. So as an example, if we want to calculate b to the 10 mod m, we can calculate b squared mod m, then b to the 4 mod m. This is our exponentiation by squaring, so that's easy. And then we can calculate b times b to the 4 or b to the 5 mod m. And then finally, we do one last exponentiation by squaring. So just in 4 computations, we've computed b to the 10 mod m. So that's wonderful. The issue is with this exponentiation by squaring. This works if b is less than the square root of the max integer, right? Because what we're doing is we're just evaluating b times b. By the way, I'm going to use this notation subscript to JS to refer to the operator in JS as distinct from the mathematical operator, which is exact, right? So b times b, and then the modulo operator modulo our modulus m. So this works fine if b is less than the square root of the max integer, because this intermediate result will also be an integer, right? So it'll also be exactly correct, because, for example, 5 squared is 25, and 25 is less than max safe integer, so it's going to be representable exactly. And this modulo function, it's important to note that the modulo function in JS is always equal to the corresponding function, the mathematical function, even if this intermediate value is greater than max safe integer. So that makes things a lot easier, actually. But here's the issue. What if b is greater than max integer, or it's greater than max integer? Then this intermediate value might go into the range where the integral values are no longer correct. So as an example, if we set b to 509,872,580, if we calculate b times b mod 5, we actually get 4 in JS, even though clearly it's divisible by 5, so b squared mod 5 is 0. Right? So how do we fix this problem? Well, we introduce a function called square mod, which takes in 2 parameters, b and m, and calculates b squared mod m. So this is just the function that we use. And this function will in turn call a function molmod, which multiplies two numbers modulo. And how does this function work? Well, first it calculates b times b. Now if b times b is less than max integer, then we just immediately return b times b mod m. Right? So that's simple. Because if it's less than max integer, the result is correct. I guess I should probably actually never mind. Absent that is necessary. Everything's positive here. However, it might not be. It might not be less than max integer. So then we do repeated addition. Just as we did repeated squaring to get exponentiation, we can do repeated addition to get multiplication. So, for example, if we wanted to do b times 10 mod m, we can first calculate 2 times b mod m, and then 4 times b mod m. This is by doubling. And then we can calculate b plus 4 times b mod m. So that's 5 times b mod m. And finally, by again another doubling, we get 10 times b mod m. So in 4 steps, we've calculated this. Obviously, that's a lot slower than it'd like to be, but it's going to be O log 2 of the arguments, right? So it's not terrible, right? Obviously, this is going to be called recursively within this. So this has a worst case scenario, right? This is going to be O log 2 squared. Yeah. But this is not terrible, right? It's better than getting the wrong answer. There's an issue though. In this 2 times, while this makes overflowing a lot less likely, it's possible that 2 times b mod m will also overflow. So if b is greater than max integer, max integer over 2, then there's a possibility that there's overflow. Well, not really, because one interesting fact is that 2 times x is always going to be, in JS, is always going to be correct if x is less than max safe integer, just because the space between consecutive floats in the range between max safe integer and 2 times max safe integer is 2. So, and this is always even, so it'll always be correct. However, the real issue is right here, when we add b, which potentially is odd, to even 4 times b, which gets rounded in the intermediate to an even number. So it'll give the wrong result, it'll be off by 1. Right? How do we fix this? We introduce a new function, namely add mod of a, b, m. Now, add mod calculates a plus b mod m. Now, first it just calculates a plus b. If it's less than max safe integer, we return a plus b mod m. That's simple. If it's greater than max safe integer, we do a pretty hacky solution. We first calculate the result of, so a plus jsb, we calculate this modulo 8. You'll see why 8 is chosen in a minute. And then we also calculate a mod 8 plus b mod 8 mod 8. Now, here's something to note. This will never overflow, right? Because a and b, we're assuming they're less than max integer. Modulo 8, it's always going to return the correct result. And what this returns is the mathematically correct value, a plus b mod 8. So this is mathematically correct. This might not be correct, might be slightly off. So what we do is we compare this, and we shift the result based on the difference. So if this, for example, was 3, and this was 5, then we know that the answer was off by 2. So then we can shift the answer by 2, and note that we would not shift a plus JSB by 2 because that would just lead to more overflow errors, or outside of the normal range errors. We actually shift a plus b mod m. So we add some shift factor s, and then again do modulo. And the shift factor s is basically we check s in the range 2 to negative 2 to 2, and we check whether this, let's call this m, call this n, we check if m plus s mod 8 equals n. And if it is, then we know that that's the correct shift, and then we apply. So add mod, kind of an annoying function that you have to implement. It's the best thing I can come up with. I'm sure there's better ways to do it. But altogether, I tested this square mod and mul mod function for random inputs between 0 and max safe integer, and I compared it versus the results from big integer, and for 1,000,000 tests every time it worked. So yeah, this is a fun challenge. JS sometimes gets on my nerves, but got it working in the end.